everybody. So I want to talk about real chains today. And what do I mean by that? Well, I mean real chains, like real polymer chains, the ones that we see and interact with all the time. So let's think back first. And let's think back to last semester when we did the light scattering assignment. Part of that was looking at one polymer sample. I think it was sample 3 or something. I don't recall exactly. But we calculated the molecular weight, and then we calculated the radius of gyration, RG. And, almost everybody got the right answer. And so if you think back to the light scattering assignment, we calculated that for this particular polymer, the molecular weight, and it was MW, is the weight averaged molecular weight because of how light scattering works. MW was about 1.6 million grams per mole. So that was a huge polymer. And if you go back to your report and you look at the results that you got, you'll notice that the molecular weight didn't really change much between samples. Now, it did fluctuate a little bit, and that's just experimental error, right? The values are going to fluctuate. But if we look at RG, we looked at it in 3 solvents. So we had MEK, methyl ethyl ketone, we had dichloroethane, and we had toluene. When we calculated RG fluctuated a lot. And this troubled some of you because you sent me an email saying like, hey, what's going on? Some of you actually in your reports pointed out why this happened, but we're going to talk in detail about why this is the case. So these values for MEK, the radius of gyration was about 42 nanometers. The radius of gyration in dichloroethane was 56 nanometers. So over 10 nanometers bigger. That's a huge change. And then in toluene, it was 53 nanometers. So why is that? Well, one piece of evidence that kind of gets at what, or leads you in the direction of why this happened, is that the second virial coefficient, which is characterizing the interactions in the system, the second virial coefficient is changing. So it's something about interactions. So that's what all of the experimental evidence is telling us. Interactions are important. All right. Now, why would you be surprised? For those of you who were surprised at this result. Well, I can tell you why I would be surprised. Because if we look at ideal chains, then we can look at what our theories tell us about them. So let's go to the simplest one, the one that we as polymer physicists use all the time, the freely jointed chain. Well, what does it tell us? Well, we could go through, if you remember the somewhat lengthy calculation for the radius of gyration, we can go through and calculate the radius of gyration. And in the freely jointed chain model, the radius of gyration is b times the square root of n divided by 6. And now already we're going to come to one of the coolest things this semester. This new software and this new approach. I can do this, and boom, we have an equation. And I can make it really, really big. So let's talk about this. This is the prediction from the freely jointed chain model. So the radius of gyration, if you just look at this equation here, what does it depend on? Depends on B, that's the Kuhn length, or the segment length. It's basically the monomer size. It depends on N, so this is the degree of polymerization. Or it's basically the molar mass, and that factor of 6 that we'll take care of later. So this is why it's surprising, right? Our theory, our freely jointed chain theory, tells us that the only thing that's going to affect the radius of gyration is going to be the Kuhn length and the molecular weight. And that doesn't agree with what we measured, because we already saw here, these things all have the same molecular weight, and because they're the same polymer, they have the same Kuhn length. But the radius of gyration is quite different. And it's different to the point where it's not just some fluctuation. It's different. So something's not present in our theory. And what's not present is the effect of interactions. So let me show you a picture about what I mean by this. So what does the freely jointed chain model tell us? Remember, I don't care about equations. We can look up equations. What's important is using the equations, coming up with equations, and then understanding in our mind what the equation is telling us, right? The exact form, this thing, it doesn't matter that it's b square root of n by 6. What's important is what it's telling us. And so what it's telling us, as I've written it here, is that interactions aren't important. So now physically, why would that be? Well, let's look. Let's draw a polymer chain, or a segment of a polymer chain. So here's one monomer, and now it's going to be attached to its buddy, the neighboring monomer. So if this is monomer 1 and monomer 2, now I want to choose, well, I don't want to choose, but I want to talk about where can monomer 3 be? Well, the chain is freely jointed, right? It can completely move without any restriction. So if this is the center, right, of that monomer, and this is the bond length, then the monomer could be along any position here. And if I drew it to scale a little bit more, one option is that the third monomer could be right here, right? So let's look at this. Let's define a bond angle. The bond angle, theta, is right there. We've talked about that to death. All right. So theoretically, and you can even see it in this case, the bond angle could approach 180 degrees. And actually, if it was exactly 180 degrees, these two monomers here would overlap. That's bad. We know that's bad. Why do we know that's bad? Because general chemistry, quantum mechanics, the Pauli exclusion principle, tells us that these things cannot occupy the same space. That's forbidden. Two objects, well, there's some details. They can't have the same quantum state, right? So they can't overlap. So there's something wrong here. The freely jointed chain is allowing these things to overlap with each other. So what's actually happening in real life is these monomers here are going to interact with each other. So this effect here, there are interactions. These things can't overlap with each other. There's some volume that's going to be excluded. So there's a volume that's excluded. And any guesses as to what we call this? We call this the excluded volume. Shocker, right? So we'll denote this by V, and I'll just put these bars on it just to keep it kind of separate, because I'll also be writing nu, the Greek letter nu. So these interactions here, I've drawn them as being repulsive, right? Because the two monomers can't overlap. They're going to get close to the point where they're going to repel each other. So they can be, these interactions, I should say, they can be attractive or they can be repulsive. Oops. Or they can be repulsive. And at very close distances, they're always going to be repulsive. So as you get to infinitely close distances, those interactions are going to be infinitely repulsive. And then at intermediate distances, they can be attractive, repulsive, or zero. Or you could think maybe the attractive part could balance out the repulsive part, or whatever. There's all kinds of cases to consider. All right. So we have to answer a couple questions first. First of all, maybe the most important one is, when do the monomers interact? That's a good question. When do they interact with each other? How about when they see each other? So monomers will interact when they see each other. In other words, when they're in close contact with each other. Okay, I'm okay with that definition. So can we calculate that? Well, we can estimate it. We can get a pretty decent estimate. So let's do that. Let's look at a polymer, and I'm going to show off some new features of the software that I've got here. Let me draw this polymer, and let's see. Boom, we have a circle. That's pretty cool. All right, so here's the polymer chain. Let me draw it inside. Here's the actual polymer inside. So this is actually what's in solution. Why did I put a circle around it? Well, we're going to call this circle the pervaded volume. It's just kind of the expanse of the polymer. It's how much physical space does that yellow object take up. So I've got that. And so this polymer chain here is going to have a size. So this thing is size R. And now if you're paying attention to the details, you might say, Dr. Horan, no, that's 2 times R. Remember, we talk about things as scaling relationships. So that factor of 2, I don't really care about. So ignore it. All right, so that's that. Of course, the pervaded volume, I can calculate what that is. The pervaded volume is going to be R cubed, at least in 3 dimensions. So let's make this general. So this is in 3D. Let's say in general, the volume will be R to the D. In dimensions greater than or equal to 2. We're going to talk about multiple dimensions here just because it's interesting. What would D equals 2 mean? Well, what is a 2-dimensional polymer? They exist. Imagine you have a surface and the polymer chain lays down flat on top of it. Then the polymer chain kind of behaves like it's 2-dimensional. So that's why we want to generalize this. And of course, in 3 dimensions, it's normal. And you could talk about 4 dimensions and 5 dimensions if you want. It doesn't exist. You can still talk about it. Okay. So that's the pervaded volume. Now let's zoom in on the polymer chain here. So let's zoom in on a section like this and see what it looks like. So here's that zoomed in region. And let me draw in some monomers. So the polymer chain kind of looks like this in that region. Of course, there's many more monomers in this, but let's just say that's what it looks like in there. So when I look at the monomers at this smaller length scale, that's basically the Kuhn length that I've drawn right there. So the monomer is going to have a volume then. So the volume of the monomer is going to be B cubed. Again, neglecting the 4/3 pi stuff, right? So it's going to be B cubed in 3D, but in general, the volume of the monomer will be B to the D power. So this gives us another quantity that we can calculate, right? In addition to just talking about the pervaded volume and the volume of the monomer and things like that, what else could we say? Well, we can calculate what is the volume of the polymer. So the volume of the polymer is what? Well, I'm going to call it V sub P for polymer. And it's going to be what? The volume of the monomer times the number of monomers that I have. So times N. And remember, these can be in D dimensions. All right. So again, what question am I trying to answer here? I'm trying to answer the question, when are the monomers going to be close enough so they see each other? Well, let's draw a system, okay? And let's calculate a certain volume fraction. So what fraction of this volume is taken up by polymer? So this system I'm going to draw, this is going to represent my experimental system. Okay, nice rectangle. Let's shrink it a little bit. I guess it's a square. So what is this? this is my system. And let's put a bunch of polymers in there. So inside the system, there's going to be a bunch of polymers like this. And let's put in some of the chains, actually. The chains look like this, just like before. And they're all floating around. So I want to define something. It's a very particular quantity. It's used quite a bit, and we're going to use it to talk about different conditions, so different limiting conditions when we're studying these samples. We're going to calculate this quantity phi star. You'll hear me call it phi star a lot. You'll also hear me call it by what it is. It's what we call the overlap concentration. Okay. So what is it? Well, let's just look here. We've got polymer chains in solution. Now, if I have a dilute solution, that will do. If I have a dilute solution, then this is what a dilute solution will look like. And let's put another one here. Okay, this is dilute. So I'll just write for now. I'm going to erase it, but this is a dilute solution. Polymer chains are far apart from each other. The monomers most likely don't see each other, and you'll see why this is. So things are just isolated. Now let's start to increase the concentration of the system. So this is no longer going to be a dilute solution in this case. So I'm going to start pasting these things together, and let me just start moving some of them. Let's move this here. Now there's going to be a point where this thing is going to get really concentrated. So I'm just moving these chains close together. And they're going to get so concentrated that their pervaded volumes will just touch like this. Let me put in a couple more. So this is getting concentrated already. In fact, I don't want to keep pasting them. So I'll shrink my system down to something like this. All right, come on, a little smaller. There we go. Okay, so now I've got this system. So this is concentrated. And this is the point that I'm looking at. This is the point where things are starting to overlap. And this is going to tell us when the monomers will start to interact with each other. So imagine that this square is completely filled up by these circles. Then at this point, I could say this is when chains just begin to overlap. So just begin. To overlap. All right. So what's the volume fraction? This will be the overlap concentration. So the volume fraction, phi star, will be the volume of polymer divided by the volume of the system. And let's just do this on a single chain basis, because you see these polymer chains now have completely taken up this square. So I could describe this in terms of one polymer chain. So let me copy this. And I'm trying to paste it, but it's not working. Okay, fine. So the volume of my system is that, which is basically the same as the pervaded volume of my polymer chain. I'm trying really to get it to scale here. All right. And then inside of this, of course, is my polymer. So what I've done is I've shrunk my system down to just look at one of these chains. But I could look at the bigger system. I'm just trying to get rid of talking about end chains, right? So I'm just looking at one chain. So this is what the system looks like at the overlap concentration. Of course, there's other chains over here and over here, but we're not going to worry about those. So if this is the case, then the volume of the polymer I can write. So go down here. the volume of the polymer is what? It's the volume of the monomer times N. And the volume of the system is going to be what? Well, it's basically the pervaded volume. It's that circle. It's a circle in here. And the pervaded volume was right here. So the pervaded volume is going to be R to the D, because we're going to look in D dimensions. So this is the overlap concentration, phi star. And it's also equal to B to the D power times N divided by R to the D. And remember, if it's on a surface, D is equal to 2. Bulk, D is equal to 3. And if you want to be a crazy theorist, you can talk about 4 dimensions, but we're not going to do that because as far as we know, they don't exist. All right. So what? Well, this is the overlap concentration. This is basically related to the probability of 2 monomers interacting. All right. So what is it? Well, let's just substitute some things in. So phi star is equal to B to the D times N divided by, well, what's R? What can I put in for the size of the chain? Well, I could go back up here and I could look at the radius of gyration. Of course, remember that from the radius of gyration, I also know that the mean squared end-to-end distance is B times the square root of n, right? So that's the end-to-end distance. So I know what R is. At least if it's an ideal chain, I know what R is. So I can go down here and I could put B times n to the 1/2 raised to the D power. And so I could do this. Of course, I've got here B to the D and B to the D. So these things will cancel. And I've got in the numerator, what, n to the 1 power. And in the denominator, I've got n to the D divided by 2 power. So this is equal to, or maybe I should back up a second and say this is approximately equal to, right? We're being kind of approximate here. We've left off the prefactor. So this is approximately equal to n to the 1 minus D divided by 2. And again, the assumption here is that D is greater than or equal to 2. So I have my overlap concentration. So phi star is approximately n to the 1 divided by D over 2. And what else? Well, if I want to know the number of contacts, so this is the probability of 2 monomers seeing each other. And if I want to know how many interacting pairs there are, so how many monomers are actually seeing each other, I can multiply phi star by n, and what this will represent is the number of interacting monomers. So let's do that. What am I going to get? So I should also say that in all of this, we're assuming that n is much, much bigger than 1. I should have said that earlier, but right, n is much, much bigger than 1. So what am I going to get? Well, if I just multiply this equation by n, then what I get is that phi star times n will be n to the 2 minus d divided by 2. Again, d greater than or equal to 2, and n much, much bigger than 1. Okay, so what, right? Why did we do this? Well, remember, the question I'm trying to answer here is, when do monomers interact with each other? When do they see each other? So they see each other according to the overlap concentration. And we're going to look at how many interacting monomers there are. And why did I leave this as D? Well, one thing, let's say that D is equal to 4. All right. How many interacting monomers are there? So this is the number. Well, the number is equal to 1. Why? Because I've got n to the 2 minus 4 divided by 2 is equal to n to the 0. So what this means is that in 4 dimensions, a polymer chain is always ideal because the monomers aren't going to interact with anybody else. All right. What about D equals 3? Well, the number of monomers that are going to interact with each other is basically going to be n to the 2 minus 3 halves. That's what? N to the 1/2 power? Yeah, n to the 1/2 power. So that's what it is. And let's just compare D equals 2. The number is going to be n to the 2 minus 2 divided by 2 is 1. So n. All right. So if monomers are interacting with each other, then it's more likely that these real chain effects, the interactions, are going to cause Rg to deviate from the ideal chain models, from the freely jointed chain model. Fair enough. So in D equals 4 dimensions, that doesn't happen. The chain is always ideal. In D equals 3 dimensions, n to the 1/2 is not small. It does exist. In D equals 2 dimensions, it's n. So I guess what I'm trying to say here is that you do have interactions, and they play a role in the size of the chain. So very interesting. Also, look at these exponents. There's going to be more interactions in 2 dimensions. So if you have something, a polymer or a protein, that's sitting on a surface, then there's going to be a higher probability of the monomers interacting with each other. And so you're going to have even more of an effect for interactions in 2 dimensions than you would in 3 dimensions. But you're still going to have an effect in 3 dimensions. Okay. So that's the, the key concept, the key underpinnings of this overlap concentration and why it's important. It's going to tell us when things are going to interact with each other, and we're going to revisit this concept over and over again. And so the next thing we have to do is we have to look at this case here. What is going on with these interactions themselves? What is the excluded volume? And that will be the topic in the next video.